Section: Introduction. In this section, we discuss the importance of automating desktop applications to enhance workforce productivity. We note that commercial robotic process automation (RPA) platforms like Automation Anywhere and Microsoft Power Automate use predefined scripts to mimic repetitive user actions through the graphical user interface (GUI). However, these script-based methods can be fragile in changing environments, as even small interface updates can disrupt the automation, leading to the need for manual adjustments and significant maintenance. As software systems become more complex, the limitations of script-based automation hinder scalability and adaptability. Recently, we have seen the rise of computer-using agents, CUAs, as a promising alternative. These agents utilize advanced large language models, LLMs, to understand various user commands, recognize GUI elements, and perform actions like mouse clicks and keyboard inputs without relying on fixed scripts. Early examples, such as UFO2, Anthropic Claude, and OpenAI Operator, show that LLM-driven agents can handle tasks that traditional RPA systems struggle with. However, current CUA implementations mainly focus on visual understanding and language reasoning, neglecting integration with desktop operating systems and application internals. This reliance on screenshots and simulated inputs has several drawbacks. Visual inputs can be noisy. Existing CUAs often do not use the operating system's accessibility features or application APIs, and simulating user inputs can disrupt the user experience. To address these issues, we pose the central research question: how can we create a robust, integrated system for desktop automation that adapts to changing interfaces, coordinates various applications, and minimizes disruption to user workflows? In response, we introduce UFO2, a new AgentOS for Windows that redefines desktop automation as a core operating system feature. Unlike previous CUAs that layer automation on top of screenshots and simulated inputs, UFO2 is designed as a deeply integrated multi-agent environment, incorporating operating system capabilities and application-specific insights into the automation process. UFO2 features a centralized coordinator called the HOST-AGENT, which interprets user commands, breaks them down into meaningful subtasks, and assigns them to specialized APPAGENTs tailored for specific applications. Each APPAGENT has access to a toolbox of application-specific APIs and a hybrid action interface that combines GUI actions with native APIs, allowing for efficient and flexible automation across multiple applications like Excel, Outlook, and Edge. To ensure reliable execution, UFO2 employs a hybrid control detection system that merges Windows UI automation APIs with advanced visual models, enabling agents to interact with both standard and custom UI elements. Additionally, UFO2 continuously updates its knowledge base with external documentation and past execution data, allowing app agents to improve their performance over time without needing retraining. We also introduce a unified execution model that combines GUI actions with application APIs, enhancing efficiency and reducing sensitivity to UI changes. To minimize delays in action planning, UFO2 features a speculative multi-action execution engine that predicts and validates action sequences quickly, reducing overhead while maintaining accuracy. To improve user experience, we have developed a picture-in-picture (PIP) interface, which allows agents to operate in a secure, separate desktop environment without interfering with the user's main session. This design addresses a significant limitation of existing CUAs. In summary, our contributions include deep integration with the Windows OS, a unified action interface that combines GUI and API interactions, a hybrid control detection system for reliable UI interaction, continuous knowledge integration for autonomous improvement, speculative execution to reduce overhead, and a non-disruptive user experience through the PIP interface. We evaluate UFO2 across over 20 real-world Windows applications, demonstrating significant improvements in success rates, efficiency, and usability compared to leading CUAs. Overall, UFO2 represents a shift from GUI scripting to structured, programmable application control, showcasing the benefits of system-level integration and design. Section Summary. In this section, we introduce UFO2, a new AgentOS for Windows that revolutionizes desktop automation by integrating deeply with the operating system, allowing for robust orchestration of applications through a hybrid GUI API action interface. Our design addresses the limitations of traditional CUAs by enabling efficient, non-disruptive automation that adapts to evolving interfaces and enhances user experience while significantly improving execution success rates and efficiency. Section: Background. In this section, we discuss the limitations of traditional desktop automation, which has relied on fragile methods to mimic human interactions with graphical user interfaces, GUIs. Commercial robotic process automation, RPA, tools, like Automation Anywhere and Microsoft Power Automate, work by recording mouse movements and keystrokes, but they depend heavily on superficial GUI elements. This makes them vulnerable to even minor changes in the user interface, requiring constant human oversight to maintain functionality. Additionally, these tools lack a deep understanding of application workflows, limiting their use to repetitive tasks in stable environments. We then introduce the emergence of computer-using agents, CUAs, which utilize advancements in large language models to interpret user commands and interact with GUIs more intelligently. Early examples, such as UFO, have shown that these models can translate natural language into GUI actions without needing pre-written scripts. However, many current CUAs are still in the research phase and face challenges that hinder their practical application. We identify several key challenges for CUAs. 1. They often interact with systems through screenshots and basic input emulation, missing out on more robust system interfaces. 2. They generally lack specific knowledge about the applications they control, treating all interfaces the same and making it hard to adapt to different tasks. 3. Their execution model can disrupt user activity by taking over the desktop session, which can be unsafe and inefficient. Despite the demand for smarter automation, existing operating systems do not provide adequate support for controlling GUI applications. This leads both RPA and CUA systems to operate on a makeshift basis, lacking a unified framework for execution and coordination. We argue that automation should be a fundamental part of the operating system. To address these issues, we present UFO2, a new AgentOS for Windows that integrates automation as a core OS feature, allowing for programmable and inspectable access to GUI controls and application APIs. UFO2 is designed to interpret natural language requests and automate tasks across various Windows applications effectively. It operates as a local service, enabling users to issue commands that are transformed into coordinated workflows. The system includes essential components for orchestration, control execution, and collaboration, functioning similarly to traditional operating systems. At the center of UFO2 is the HOSTAGENT, which interprets user requests and manages system state. It delegates tasks to specialized modules called APPAGENTs, each tailored to a specific application. These APPAGENTs handle all necessary logic to control their respective applications. When a user request is received, HOSTAGENT breaks it down into subtasks and activates the relevant APPAGENTs, launching applications as needed. Each APPAGENT continuously monitors application states and determines the next steps through a structured planning process. This cycle continues until the task is completed or an error occurs. UFO2 facilitates communication between HOSTAGENT and APPAGENTs through a shared interface, allowing for complex workflows across different applications without the need for custom scripts. Importantly, all operations occur in a safe, isolated environment, ensuring that multiple applications can run concurrently without interference. Section Summary. In this section, we discuss the limitations of traditional desktop automation tools, which rely on brittle techniques and lack adaptability, leading to frequent maintenance needs. We introduce UFO2, a new AgentOS for Windows that integrates automation as a core OS abstraction, enabling robust, natural language-driven task automation across multiple applications while addressing issues of reliability, application introspection, and safe execution. Section: Design Rationale, Centralized Multi-Agent Runtime. In this section, we discuss the design rationale behind UFO2's centralized multi-agent runtime. We utilize a centralized host agent to enhance both reliability and extensibility. This HOST agent acts as a control center, making it easier to manage tasks, handle errors, and oversee the lifecycle of applications. Each AppAgent, on the other hand, is designed as a loosely connected executor that contains specific application functions. This modularity allows us and third-party developers to gradually enhance UFO2 by creating new application interfaces and API connections. These agents can be discovered, are self-sufficient, and can be activated by the runtime as needed. This separation of roles helps ensure that application logic can develop independently from the main task management system. Together, the HOST agent and AppAgent framework allows UFO2 to serve as a scalable and flexible platform for CUA automation, simplifying the complexities of different interfaces and providing a consistent system interface for structured application behavior. The HOST agent is the main control unit of UFO2. It interprets user goals, breaks them down into manageable subtasks, activates AppAgent modules, and coordinates their activities throughout the system. It offers services for system introspection, planning, managing application lifecycles, and synchronizing multiple agents. The HOST agent operates on the Windows platform, overseeing active applications, issuing commands to start new processes, and managing the creation and removal of AppAgent instances. All coordination is handled through a persistent state machine that directs the transitions between different execution phases. To perform its control tasks, the HOST agent combines two layers of system awareness: the visual layer, which captures detailed screenshots of the desktop to understand layouts, and the semantic layer, which uses Windows UI automation APIs to gather structural information about applications and their components. This dual approach helps the HOST agent clarify uncertainties, identify inconsistencies during runtime, and make informed decisions for the agents. The HOST agent generates structured outputs to guide subsequent actions, including a high-level execution plan that outlines the subtasks, shell commands for managing application lifecycles, the name and index of the application for the next AppAgent, context-specific instructions for AppAgents, interactive prompts for user clarification, and the current state of the HOST agent. The core logic of the HOST agent is structured as a finite state controller with several states: continue, where it checks which subtasks can start or resume; assign, where it selects an application and launches the corresponding app agent; pending, where it waits for user input; finish, where it cleans up after all subtasks are done; and fail, where it enters recovery mode if a failure occurs. This clear state structure allows the HOST agent to effectively manage dynamic workflows while ensuring task completion and fault isolation. The HOST agent also maintains two types of persistent state: private state, which tracks user intentions and session progress, and a shared blackboard, which is a memory space that allows agents to communicate by recording important observations and results. This separation keeps local context contained while providing a consistent view for all agents, facilitating collaborative task execution. Overall, the HOST agent simplifies the management of complex workflows across applications, enabling modular execution and effective task management, which are essential for scaling desktop automation. The AppAgent serves as the main execution unit in UFO2, responsible for completing specific subtasks within a Windows application. Each AppAgent operates as an independent worker process, tailored to a single application and knowledgeable about its API and control logic. When it receives a subtask from the HOST agent, the AgentOS starts a control loop that senses the application state, determines the next action, and executes either a GUI or API-based command. This hybrid approach, using a puppeteer interface, allows for reliable control over complex user interfaces by prioritizing structured APIs while still being able to interact through the GUI when necessary. Section Summary. In this section, we describe UFO2's centralized multi-agent runtime, where the host agent orchestrates tasks and manages application lifecycles, while agents execute specific subtasks tailored to individual applications. This architecture enhances reliability, extensibility, and modularity, allowing for dynamic execution and robust management of complex workflows in desktop environments. Section: Perception Layer. In this section, we describe the perception layer of our agent, which combines various streams of perception. First, we capture visual input through screenshots of the graphical user interface, GUI, to understand the layout and control elements. We also extract semantic metadata from Windows UI automation APIs, which includes details like control type, label, hierarchy, and whether the control is enabled. Additionally, we use set-of-mark techniques to annotate controls on these screenshots. By merging these signals, we create a structured observation object that includes both the GUI screenshot and potential control elements, allowing for a deeper understanding of the application state beyond just visual input. Next, based on this understanding, the agent generates a structured output that includes the target control, if relevant, the type of action to take, like clicking or typing, any necessary arguments, a reasoning trace, and the current state in a local finite state machine, FSM. This design separates perception from action, which helps with deterministic replay, offline debugging, and detailed observability. Each agent operates with a local finite state machine that dictates its behavior in the application context. The states include continue for ongoing actions, pending for actions needing user confirmation, finish for completed tasks, and fail for unrecoverable errors. This model confines failures to the current task, allowing for safe interruptions, retries, or delegations, and supports workflows that can resume from checkpoints. To maintain contextual awareness, each agent keeps a private state log of actions and decisions, as well as a shared state that updates the system-wide blackboard with outputs, errors, and insights. This dual memory system allows app agents to function independently while staying in sync with the overall system, enabling composability where one agent's output can serve as another's input for subsequent tasks. We also provide an application-aware SDK to facilitate the quick onboarding of new applications. Developers can register specific APIs through a straightforward interface, including function details and argument structures. They can also add domain-specific help documents to a searchable knowledge base for agents to access during runtime. This modular approach allows third-party developers to enhance UFO2's capabilities without needing to retrain models, as new features can be added by updating the agent module for the application. In summary, each agent acts as a per-application execution runtime, offering modular and domain-aware control that is more efficient and robust than generic GUI agents. Its hybrid perception action loop, extensibility through plugins, and local fault management enable UFO2 to scale effectively across large application ecosystems with minimal disruption. We also address the challenge of reliably perceiving GUI elements, which is crucial for app agents to interact safely with application interfaces. Given the diversity in real-world GUI environments, where some applications provide structured accessibility data while others do not, we introduce a hybrid control detection subsystem. This system combines UIA-based metadata with vision-based grounding to create a comprehensive control graph for each application window. When UIA data is available, we utilize it to extract controls with specific attributes, forming an initial control graph. To enhance this, we integrate a vision-based model called OmniParser v2, which quickly identifies additional interactive elements in application screenshots. Each detection includes the control type, confidence score, and spatial details. We then merge these two data streams, removing duplicates based on bounding box overlap. Visual detections that overlap significantly with UIA-derived controls are discarded, while remaining visual-only detections are transformed into pseudo-UIA objects for seamless integration into the APPAGENT pipeline. This combined control set is then passed to the annotation module, creating a unified actionable control graph for the APPAGENT to use. Section Summary. In this section, we describe how each APPAGENT integrates multiple perception streams, including visual input and semantic metadata, to create a comprehensive understanding of the application state. We also outline the structured output and execution model, which utilizes a finite state machine for behavior management, and highlight the hybrid control detection system that combines UIA data with vision-based methods to ensure reliable interaction with diverse GUI environments. Section: Unified GUI API Action Orchestrator. In this section, we discuss the Unified GUI API Action Orchestrator. Our APPAGENTs can work with application environments that offer two types of interfaces: GUI frontends, which are easy to see but can be fragile, and native APIs, which are more reliable but need specific integration. To bring these different execution methods together, we introduce the Puppeteer, a flexible execution orchestrator that chooses between GUI automation and application-specific APIs for each action step. This approach enhances task reliability, reduces delays, and makes maintenance easier. For tasks that usually require lengthy GUI interactions, like formatting cells in Excel, we can often simplify them into a single API call, which speeds up execution and lowers the chances of failure. The Puppeteer allows developers to register high-level operations in target applications easily using a simple Python decorator. Each function is tagged with important information and added to the APPAGENT's action space. During execution, UFO2 prompts the APPAGENT to decide the best execution path. If a suitable API is available, we prefer it for its reliability. If an API fails or isn't available, we can switch to GUI control through simulated clicks or keystrokes, maintaining robustness across different environments. Next, we leverage existing documentation from desktop applications, such as user guides and online tutorials. UFO2 provides a one-click option to parse these documents into a specific vector store. The documents are organized with natural language descriptions and execution guidance. When an APPAGENT faces a subtask, it queries this store for relevant guidance, which helps it handle new applications or infrequent tasks by enriching its context with practical knowledge. Additionally, we continuously learn from our execution history. Each automation run generates structured logs that include task descriptions, action sequences, screenshots, and outcomes. We periodically analyze these logs to create reusable example records that contain task signatures and step-by-step plans. When similar tasks arise, the APPAGENT uses in-context learning to retrieve relevant examples, enhancing execution accuracy without the downsides of fine-tuning. At the system level, we integrate a knowledge layer that acts as a retrieval augmented generation (RAG) component, connecting pre-trained language models with application-specific needs. Both help documents and examples are indexed for quick retrieval, ensuring that our knowledge remains current with software updates. This integration transforms our agents from rigid constructs into adaptable, evolving systems, supporting sustainable automation across diverse application environments. Finally, we address a common issue in conventional CUAs, where each automation step is executed separately, leading to delays and increased resource use. To tackle this, we introduce speculative multi-action execution, which allows us to predict multiple likely actions in one go and validate them in real time. This method involves 3 stages: predicting actions with a single query, validating each action's conditions using the Windows UIA API, and executing them sequentially while stopping if any validation fails. This approach significantly reduces the frequency of LLM calls and spreads the planning cost across multiple actions, all while ensuring correctness through reliable validation. Section Summary. In this section, we describe how UFO2's Puppeteer orchestrates actions by dynamically choosing between GUI automation and native APIs, enhancing task robustness and reducing execution time. We also explain our approach to leveraging task-level documentation and execution history for continuous learning, while introducing speculative multi-action execution to minimize latency and improve reliability through runtime validation of actions. Section: Picture-in-Picture Interface. In this section, we discuss the Picture-in-Picture (PIP) interface, a key feature of UFO2 designed to enhance automation while maintaining a responsive user experience. Traditional user control applications often take over the workspace, making the system unusable during tasks. To address this, we created the PIP interface, which is a lightweight virtual desktop window that allows automation to run alongside user activities without disruption. The PIP interface is different from standard applications as it provides a resizable and movable window that mirrors the user's desktop. It operates using Windows Remote Desktop Protocol loopback, creating a separate virtual session on the same machine. Applications within this PIP session use the user's identity and settings, ensuring a seamless experience. The PIP window acts like a sandbox, allowing automation to run in the background while the user maintains full control of their primary desktop. To ensure clear separation between user actions and automation, we utilize the RDP subsystem to keep input and device contexts distinct. Mouse and keyboard inputs in the PIP are confined to that session, preventing interference with the main desktop. This isolation is crucial for maintaining stability during simultaneous activities. Additionally, any errors in the PIP do not affect the primary desktop, protecting the user's environment. We also establish a secure communication channel between the PIP and the host environment using Windows-named pipes, which are authenticated and encrypted. This allows for two-way messaging, enabling task assignments and status updates without needing direct access to the PIP window. This setup enhances usability and trust, especially in long-running tasks. The PIP interface is not just a user experience improvement. It represents a system-level solution that balances automation, usability, and safety. It separates automation from user interaction, introduces new isolation methods for GUI agents, and simplifies error recovery. We built UFO2 as a comprehensive desktop automation framework with over 30,000 lines of Python and C# code. Python handles the core functions, while C# supports the GUI and Windows-specific tasks. We also use sentence transformers for enhanced document retrieval. UFO2 employs a session-based execution model that allows for iterative workflows. Each session retains context, enabling users to refine tasks and intervene when necessary. This approach supports human oversight and helps tackle complex tasks effectively. To address the risks associated with automation, we implemented a safeguard mechanism that detects potentially harmful actions. If an action is deemed risky, the agent pauses and prompts the user for confirmation before proceeding. This customizable safeguard system allows users to define what constitutes a risky action, enhancing safety and trust in real-world applications. Section Summary. In this section, we describe the Picture-in-Picture (PIP) interface of UFO2, which allows high-throughput automation without disrupting the user's primary desktop environment by enabling isolated agent execution in a virtualized window. We also highlight the system's robust input isolation, secure communication, and safeguard mechanisms that enhance usability, safety, and user control during automation tasks. Section: Everything as an App Agent. In this section, we discuss the everything as an app agent concept. To enhance ecosystem flexibility, we introduce an agent registry that allows us to integrate various third-party components as pluggable app agents. By using a straightforward registration API, we can wrap external automation tools, like specialized copilots, with lightweight compatibility layers that provide a consistent interface to the HOST-AGENT. This setup allows the HOST-AGENT to treat both native and external APP-AGENTs similarly, assigning tasks based on their capabilities. We observe that even simple wrappers, such as for the OpenAI operator, can lead to noticeable performance improvements, showcasing the system's modularity and its capacity to incorporate different execution backends with minimal effort. Next, we describe our AgentOS as a service model. We utilize a client-server architecture for effective large-scale deployment. A lightweight client on the user's machine manages the graphical interface and application sensing, while a centralized server, either on premises or in the cloud, runs the HOST-AGENT and APP-AGENT logic, coordinates workflows, and processes LLM queries. This separation provides several advantages. It enhances security by isolating sensitive operations from user devices, allows for easy server-side updates without client modifications, and supports multiple clients through centralized scheduling. This client-server structure promotes modularity and simplifies deployment in enterprise settings. We also emphasize the importance of a comprehensive logging and debugging system. To support ongoing improvements and diagnose issues, we implement a detailed logging framework that captures execution traces, including prompts, outputs, control data, interface states, and errors. At the end of each session, we compile these into a structured log in Markdown format. This allows developers to review agent decisions, visualize state changes, and replay actions for debugging. The framework also enables prompt editing and targeted replay for hypothesis testing, speeding up the debugging process. This observability layer acts as a lightweight tracking system for agent behavior, enhancing transparency and accountability during deployment. Additionally, we include an automated task evaluation engine that uses LLMs to provide structured feedback for continuous improvement. This evaluator analyzes session traces, breaking down tasks into evaluation criteria and assigning scores to determine success, partial success, or failure. The results feed into dashboards and debugging tools, facilitating self-monitoring and offline analysis of failures, thus closing the loop between execution and improvement. In summary, these engineering components reflect our commitment to operational robustness and extensibility. From session-based execution and pluggable agents to service-oriented deployment and observability infrastructure, each module is designed to connect LLM agent concepts with practical deployment realities. For evaluation, we rigorously tested UFO2 across over 20 Windows applications, including Office suites and custom tools, to measure performance and efficiency. Our findings indicate that UFO2 achieves a 10% higher task completion rate and a 50% improvement over the best current CUA operator, thanks to deeper integration with the operating system. The hybrid UIA vision approach successfully identifies custom GUI elements that UIA alone might miss, improving success rates with proprietary widgets. Allowing app agents to use native APIs or GUI interactions enhances completion rates by over 8%, reduces latency, and minimizes the fragility of click-based workflows. Utilizing external documents and execution logs boosts UFO2's ability to manage unfamiliar features without needing retraining. Speculative multi-action execution combines multiple steps into a single LLM call, cutting inference costs by up to 51.5% while maintaining reliability. By enabling everything as an app agent, we enhance overall performance and maximize the potential of each agent. These results confirm that UFO2's deeper integration with Windows and application-level APIs leads to higher performance and lower overhead, supporting an OS-native approach to desktop automation. Finally, we note that our benchmark environments are set up on isolated virtual machines with 8 AMD Ryzen 7 CPU cores and 8 GB of memory, reflecting typical deployment conditions. We access all GPT family models through Azure OpenAI services, while the OmniParser V2 Vision model runs on a separate virtual machine equipped with an NVIDIA A180 GB GPU for efficient visual processing. Section Summary. In this section, we describe UFO2's architecture, which includes an agent registry for integrating third-party components as pluggable APPAGENTs, a client-server model for scalable deployment, and a comprehensive logging framework for enhanced observability and debugging. Our evaluation demonstrates that UFO2 significantly improves task completion rates and efficiency through deeper OS integration and innovative execution strategies, making it a robust solution for desktop automation. Section: Benchmarks. In this section, we evaluate UFO2 using two well-known benchmarks focused on Windows automation. The first benchmark, Windows Agent Arena, WA, includes 154 live tasks across 15 popular Windows applications, such as Office tools, web browsers, and multimedia apps. Each task has a custom script to check for correctness. The second benchmark, OS World W, is a specific subset of OS World, featuring 49 tasks related to Office applications, browser interactions, and file operations, also with verification scripts. We compare UFO2 against 5 advanced automation systems that use GPT-4o for inference. These include UFO, a multi-agent system for Windows; Navi, a single-agent system from WA; OmniAgent, which combines visual grounding with action planning; AgentOS, which uses a multi-agent approach for complex tasks; and Operator, a recent high-performance system from OpenAI that mimics human interactions. We chose these systems to represent various design approaches, ensuring fairness by limiting each agent to 30 execution steps per task. We also assess a basic version of UFO2, called UFO2 Base, which uses only UI automation and GUI interactions without dynamic knowledge integration. In contrast, the full UFO2 implementation includes hybrid control detection and continuous knowledge updates. We selectively integrated APIs for 3 Office applications in OS World W but did not add any for WA tasks. For our evaluation, we use 2 main metrics: success rate, SR, which measures the percentage of tasks completed successfully, and average completion steps, ACS, which counts the average number of steps taken per task. A lower number of steps indicates higher efficiency, which is crucial for practical automation. Our results show that even UFO2 Base, which relies on standard UI automation, outperforms previous state-of-the-art systems. With GPT-4o, UFO2 Base achieves a 23.4% success rate on WA, surpassing Operator by 2.6%. When using the stronger O1 model, this rate increases to 25.3%. The full version of UFO2, with its advanced features, reaches a 27.9% success rate on WA, significantly exceeding Operator's 20.8%. On OS World W, UFO2 achieves a 28.6% success rate, effectively doubling Operator's 14.3%. Using the O1 model further boosts UFO2's performance to 30.5% on WA and 32.7% on OS World W, highlighting the benefits of its deep integration with operating system mechanisms. We also provide a detailed breakdown of success rates by application type, revealing that UFO2 performs particularly well in web browsers and coding environments. For example, with the strongest configuration, UFO2 achieves a 40.0% success rate for web browser tasks, outperforming OmniAgent by over 12%. In coding tasks, UFO2 reaches a 58.3% success rate, significantly higher than all other systems. These findings emphasize the effectiveness of UFO2's hybrid approach and continuous knowledge integration, which enhance action inference and reliability in complex workflows. We note that tasks involving LibreOffice yield lower success rates due to limited accessibility support, while tasks using Microsoft 365 applications show improved rates due to better API availability. Cross-application tasks present additional challenges, requiring sophisticated coordination. Here, UFO2's multi-agent architecture shows promise, achieving a 9.1% success rate, which, while modest, demonstrates the potential of coordinated multi-agent systems in tackling complex scenarios. Overall, Our results validate UFO2's design principles, particularly its focus on deep integration with operating systems and applications, multi-agent collaboration, and flexible action orchestration. While there is room for improvement in less supported application areas, UFO2 already offers significant advancements in practical desktop automation. Section Summary. In this section, we evaluate UFO2 against established Windows automation benchmarks, demonstrating its superior performance compared to state-of-the-art CUAs, particularly in complex tasks requiring deep OS integration. Our results highlight that UFO2's hybrid GUI API approach and multi-agent architecture significantly enhance task reliability and efficiency, achieving notable success rates across various application types. Section: Error Analysis. In this section, we analyze the errors encountered by UFO2 to better understand its limitations and identify areas for improvement. We manually reviewed all failure cases for UFO2 based on both benchmarks, categorizing each failure into three main types. 1. Plan errors. These occur when the agent misunderstands the task, leading to incomplete or incorrect action plans. This suggests that the agent lacks a clear understanding of the task or the specific workflows involved. 2. Execution errors. These happen when the overall plan is sound, but the execution is flawed, such as choosing the wrong control or performing unintended actions. These errors often arise from poor visual reasoning or incorrect associations between interface elements and actions. 3. Control detection failures. These are instances where the agent fails to recognize essential interface controls needed to complete a task, often due to non-standard UI elements that aren't accessible through typical operating system APIs. Our findings indicate that over 62% of failures in the WA benchmark were due to control detection failures, revealing significant gaps in UI accessibility, especially with third-party applications. In contrast, the OS World W benchmark showed more plan errors, indicating that these tasks often require more complex workflows and deeper understanding. These insights highlight specific weaknesses in the system, which have driven the enhancements in the full version of UFO2. The high rate of control detection failures supports our decision to implement a hybrid detection approach that combines standard UI data with advanced visual techniques. Similarly, the prevalence of plan errors emphasizes the need for richer external documentation and domain-specific knowledge to improve task understanding. Next, we evaluate the effectiveness of our hybrid control detection strategy. We introduced a control recovery ratio to measure how many failures that were only detected by UIA were successfully completed using either the Omni parser or our hybrid method. Our results show that the hybrid approach consistently outperforms the other methods, improving the overall success rate and converting nearly 10% of previously unrecoverable cases into successful completions. We also assess the integration of API actions with standard GUI interactions in our Puppeteer framework. We focused on 27 Office-related tasks and developed 12 APIs for applications like Word, Excel, and PowerPoint. These APIs simplify complex multi-step GUI tasks into single calls, enhancing performance. Our comparison of success rates and error recovery rates between GUI-only and GUI plus API configurations shows that integrating APIs significantly boosts success rates and reduces the number of steps needed to complete tasks. Overall, these findings confirm the benefits of combining GUI automation with API calls, highlighting the importance of deep integration for effective desktop automation. Section Summary. In this section, we conducted a detailed error analysis of UFO2, categorizing failures into plan errors, execution errors, and control detection failures, with over 62% of failures on the WA benchmark attributed to the latter due to gaps in UI accessibility. Our findings highlight the effectiveness of a hybrid detection approach and the integration of API actions with GUI interactions, which significantly improved task completion rates and reduced the number of steps required for successful task execution. Section: Case Study. In this section, we illustrate how our GUI and API approach simplifies task execution. We present a case where we export an Excel file to CSV format using OS World W, comparing GUI-only interactions to those that combine GUI and API. While both methods succeed, the GUI-only approach requires 5 steps to open the save dialog, choose the file format, and confirm the action. In contrast, we can complete the task instantly with a single call to the save_as API. This not only boosts efficiency but also minimizes the risk of errors that can accumulate through multiple GUI interactions, showcasing the benefits of deeper integration at the OS and application levels. Next, we evaluate the impact of continuous knowledge integration on UFO2's performance. We enhance UFO2 with external documentation and insights from execution to improve its understanding of tasks without needing retraining. We create 34 help documents with detailed instructions for benchmark tasks, allowing UFO2 to access the most relevant guidance during execution. Additionally, we set up an automated system that summarizes successful task executions, which are validated and stored in a knowledge database. For future tasks, UFO2 can retrieve up to 3 relevant past execution logs to assist in planning and execution. We measure the effectiveness of this knowledge integration using the Plan Recovery Ratio, PRR, which indicates how many previously failed planning cases are resolved with new knowledge. Our results show significant performance improvements, with reductions in planning failures by up to 17.7%. While help documents provide modest gains, their effectiveness varies with task complexity. Overall, our findings highlight the importance of systematic knowledge integration, showing that continuously enhancing the agent's knowledge base can greatly improve its reliability and adaptability in real-world applications. We then assess how speculative multi-action execution influences task completion rates and efficiency. We compare 2 modes for UFO2, executing one action at a time versus inferring multiple actions in one step. Our analysis focuses on tasks completed successfully by both modes. The results indicate that speculative multi-action execution maintains a similar success rate while significantly reducing the average number of steps, by up to 10% on WA and an impressive 51.5% on OS World W. Since each step requires a call to the language model, fewer steps lead to lower latency and costs. This confirms that speculative multi-action planning enhances efficiency without sacrificing reliability, further demonstrating UFO2's capability to optimize resource use in desktop automation. We also provide a practical example of speculative multi-action execution. When a user asks UFO2 to center align a heading in a Word document, the usual steps would involve selecting the text and clicking the center icon. Instead of treating these as separate actions, UFO2 predicts both in one step, using speculative multi-action planning. This allows us to complete the task with just one call to the language model, significantly improving efficiency while ensuring accuracy. Finally, we explore the everything as an app agent capability. We conducted an experiment where UFO2's host agent uses only the operator as the AgentOS, disabling all native app agents. The operator then accepts subtasks and communicates through the standard UFO2 messaging protocol, with its perception limited to screenshots of the selected application window. Our results show that UFO2 combined with the operator achieves higher success rates than the operator alone, especially on WA. We attribute these improvements to 3 main factors. The HOSTAGENT clarifies complex instructions into simpler subtasks, provides additional tips to enhance decision-making, and limits the operator's view to reduce visual clutter. These findings highlight the advantages of UFO2's multi-agent design and demonstrate how the everything as an app agent approach can enhance the performance of existing user control applications. Section Summary. In this section, we illustrate how the GUI plus API approach enhances task execution efficiency, showing that a single API call can complete tasks faster and with fewer errors compared to a multi-step GUI process. We also evaluate the impact of continuous knowledge integration on UFO2's performance, demonstrating that augmenting its knowledge base significantly reduces planning failures and improves adaptability in real-world applications. Section: Efficiency Analysis. In this section, we analyze the efficiency of UFO2 by profiling its task execution, focusing on step count and latency. For step count profiling, we summarize the average execution steps taken by the HOST AGENT and APP AGENTs across benchmark suites. We ensure that the steps are based on successfully completed tasks for fair comparisons. We find two main insights. First, the fully integrated UFO2 configuration consistently requires fewer steps than the baseline UFO2 base, with reductions of up to 50%. This improvement shows that deep OS integration, particularly through hybrid GUI API orchestration and advanced control detection, streamlines execution. Second, using a more powerful reasoning model, like O1 compared to GPT-4o, further decreases step counts. This suggests that better reasoning allows the agent to find more efficient action sequences, such as utilizing direct API interactions and avoiding unnecessary GUI steps. This highlights the importance of both strong system integration and advanced reasoning in reducing execution time. For latency breakdown, we provide a detailed view of average latency per execution step in UFO2, divided into 5 phases: I. Screenshot capture, E. Control detection via UIA APIs and Omni parser v2, E. Prompt preparation, IV. LLM inference, and V. Action execution. The LLM inference phase takes the most time, averaging around 10 seconds per inference, indicating a need for optimization through smaller models or better hardware, which we haven't evaluated yet. Excluding this inference time, the baseline UFO2 base executes efficiently at about 10 seconds per step, while the fully integrated UFO2 adds only 1 second per step due to its hybrid control detection, which enhances GUI control detection accuracy at a small latency cost. Overall, the reduction in steps keeps task completion times practical, around 1 minute per task, showing that UFO2 balances latency, accuracy, and efficiency well for desktop automation. In our model ablation analysis, we compare UFO2 and UFO2 base across 4 large language models. Models like GPT-4v and GPT-4o provide direct answers without showing reasoning steps, while Gemini 2.0 and O1 incorporate reasoning internally. Generally, models with built-in reasoning achieve higher success rates, emphasizing the benefit of more thoughtful processes in desktop automation. This suggests a promising path for CUAs, fine-tuning advanced reasoning models for desktop tasks. By allowing agents to create and refine multi-step plans, especially with deeper OS signals, UFO2 can handle complex situations more effectively. As LLM reasoning improves, we anticipate further enhancements in accuracy and versatility from UFO2's adaptable design. Regarding latency and responsiveness, UFO2 currently performs LLM inference at each decision step, leading to latencies of several to tens of seconds per action. Despite optimizations, complex tasks can take 1 to 2 minutes, which is acceptable but still slower than skilled humans. To reduce perceived delays, we introduced a picture-in-picture interface, allowing UFO2 to run tasks in a separate virtual desktop, minimizing user disruption during longer automations. In future work, we plan to lower latency further by exploring specialized, lightweight large action models optimized for specific tasks to improve responsiveness and scalability. Finally, our evaluations show that while UFO2 is effective, it does not yet consistently match human-level performance across all Windows applications. To close this gap, we need to focus on 2 key areas. First, improving foundational visual language models by fine-tuning them on diverse GUI interaction datasets to enhance agent capabilities. Second, integrating more closely with OS-level APIs and structured documentation to improve contextual understanding and execution reliability. Given UFO2's modular design, we can implement these improvements gradually, continuously enhancing performance towards human-equivalent proficiency across various applications. Section Summary. In this section, we analyze the efficiency of UFO2 by profiling task execution, revealing that its fully integrated configuration reduces execution steps by up to 50% compared to the baseline, while enhanced reasoning models further optimize action sequences. We also identify latency bottlenecks, particularly in LLM inference, and propose future improvements to bridge the gap towards human-level performance through better model training and OS integration. Section: Generalization across operating systems. In this section, we discuss how UFO2 primarily targets Windows OS due to its large market share, but its modular design allows for easy adaptation to other systems like Linux and macOS. Our approach uses accessibility frameworks, which have equivalents on these platforms, enabling us to apply our design principles and strategies for quick customizations. We see exploring cross-platform capabilities as a key area for future work, aiming to create a unified ecosystem for desktop automation across different environments. We also highlight the growing field of integrating large language models, LLMs, into operating systems, focusing on their role in system-level integration for desktop automation agents. Recent advancements in multimodal LLMs have led to the development of computer-using agents, CUAs, that automate workflows by mimicking GUI interactions. Early systems like UFO utilized multimodal models and UIA APIs to interpret interfaces and perform tasks through natural language. UFO introduced a multi-agent architecture that improved the reliability of CUAs for complex workflows. Subsequent projects have refined these models and expanded their capabilities. For instance, CogAgent specialized in GUI understanding across various platforms, while industry interest has grown with agents like Anthropic's CLAUDE 3.5 and OpenAI's Operator, which enhance desktop automation. However, many existing CUAs are still prototypes and lack deep OS integration. Our work with UFO2 addresses these limitations through a modular architecture and better integration with OS and APIs, bridging the gap between theoretical CUAs and practical automation. We also explore the idea of embedding LLMs directly into OS architectures to improve automation and usability. Zhe et al. proposed the AgentOS framework, placing an LLM at the core of OS design to facilitate user interactions and decision-making. Building on this, May et al. created a prototype that integrates LLM interactions within the OS kernel, providing essential functionalities while simplifying agent development. Rama et al. further expanded this by introducing semantic file management through AgentOS agents. Additionally, AutoOS applied LLMs for automatic tuning of Linux kernel parameters, showcasing how LLMs can enhance system performance. Overall, these research efforts indicate a shift towards making LLMs integral to operating systems, enabling powerful automation and improved user interaction. Our work with UFO2 specifically targets desktop automation, offering a scalable and practical AgentOS that utilizes multimodal LLMs alongside robust OS mechanisms.